5 questions, and it is due the day after we finish the lesson, so Monday.
Yes. Probably.
What?
It won't.
No.
You said 2 lessons. You said 2 days.
One of them might take a whole page.
Oh, great.
One of them might. I make no promises.
Wait. If I make this pencil, you gotta take that.
This is the wrong one. This is the one I like.
This one is
Not be on track today.
every day. Oh my. But he's great. It's just, that's what, I guess that's how this can help us here.
Did you get your hand all over today, right?
No, I did not. Yeah, one of them might take a hot minute because I don't find
Did your hand ever cramp up from writing so much just for math?
this exact example starts here and then goes here and most of this page. So it can theoretically take that long. Not trying to scare you or anything, because it's really not that bad. It just takes a hot minute. Okay.
Too late.
So to get this started, we are going to talk about the theorem of conjugate pairs of a polynomial. So this theorem says, if a polynomial of degree greater than 1 has real coefficients and if one of my zeros is the complex number a plus bi, where b is not equal to 0, then its conjugate, a minus bi, where b does not equal 0, is also a 0. Z just means 0. That's what I'm saying.
Oh, I figured you would have converted to 0.
So of course we're going to do a lovely example of this. I heard that hefty sigh.
Whenever I read this,
Wait,
like when I'm starting,
just move it up again.
Yeah, I'm just moving it up. I'm not getting rid of it.
whenever I'm reading this, like when I'm starting homework, I completely forget everything, and I'm just clueless on the read. So it's kind of hard.
So the example we're going to do is to find the polynomial f of x of degree 4 that has real coefficients in zeros 2 plus I and negative 3i. So as I'm looking at this problem, how many zeros do I need to have in total? Everybody.
4.
4, because it is a degree 4 polynomial. How many have I been given? 2, but each of those is a complex number, which means the conjugate of each of those is also a 0. So because 2 plus I is a 0, so is 2 minus I. And because negative 3I is a 0, so is positive 3I. I now have 4 zeros. They're all complex, but I still have 4 of them. And from here, I can build my polynomial. So the first thing I want to do once I have my zeros is I want to write them as x equals whatever that 0 is. So here I have x equals 2 plus I and x equals 2 minus I. Then I'm going to have x equals negative 3I and x equals 3I. I need to manipulate these so that they are no longer written as zeros, but as factors, which means I want that right-hand side to go to 0. What am I going to have to do with the 2 plus I to make that right-hand side equal 0? Subtract it over to the left. So this is the same as x minus 2 plus I equals 0. And then we can distribute the negative into that. Same thing over here. I'm going to have x minus 2 minus I equals 0. Same thing here. I add the 3I over. And on this one, I subtract the 3I over. I now have 4 factors that I will use to build my degree 4 polynomial. So I go ahead and I write them out. So I have x minus the quantity 2 plus I times x minus the quantity 2 minus I times x plus 3I times x minus 3I. I'm going to have to do this in groups of 2. So I'm going to FOIL out my first 2 factors, and then I'll FOIL out my third and fourth factors. So I'm going to use hard brackets to split those up.
Why didn't you distribute the first?
We're going to in a second. I just like to keep it here so you see the connection, and then we'll distribute the negative. So this is the same as having x minus 2 minus I times x minus 2 plus I on the left-hand side, which means I can go ahead and just FOIL this out. What's x times x?
6 squared.
X squared. X times a negative 2 is negative 2x. X times I is xi. Negative 2 times x is negative 2x. Negative 2 and negative 2 is positive 4. Negative 2 and I is negative 2i. Negative I times x is negative xi. Negative I times a negative 2 is positive 2i. And negative I times I is negative I squared. This was all just from FOILing out those first 2 factors. I'm going to go ahead and simplify this as much as possible. Is there anything I got that canceled out?
2i plus 2i.
Negative 2i and 2i. Also my xi's. I heard somebody say that. Nothing else canceled, but I can put stuff together. Right? I have a negative 2x and a negative 2x, which becomes negative 4x. The x squared comes down because it can't combine with anything. I have a plus 4, and then I have a minus I squared.
You can simplify the I squared.
How can I simplify the I squared, Becca?
Negative 1.
I squared is equal to negative 1. So then that negative turns into a positive. And this is the same as plus 1, which I will then combine with the plus 4. And those 2 imaginary numbers created the quadratic x squared minus 4x plus 5. But this was only half of my original polynomial. Don't worry, the other half is significantly easier. So then I go to my second group of factors, and I do the same thing, except they are each binomial, so I can do normal foiling here, and it won't take as long. So what's x times x? X times a negative 3i is negative 3xi. 3i times x is a positive 3xi. And 3i times a negative 3i is a negative 9i squared. I go ahead and I simplify this. The x squared cannot combine with anything. The 3xi's cancel each other out. What happens to negative 9i squared? Becomes positive 9. So then I can go ahead and put my two factors next to each other. And then I'm almost done.
Wow.
Now I get to FOIL out the two quadratics that I created from these imaginary numbers.
That's hilarious.
That's funny that you think I'm joking. So then let's go ahead and do this. I know we're just loving this. X squared times x squared.
X to the 4.
X squared times 9. Negative 4x times x squared. Negative 4x times 9.
Negative 36x.
5 times x squared. And 5 times 9. We go ahead and we combine like terms. The only ones I can put together are the 9 and the 5x squared, which gives me x to the 4th minus 4x cubed plus 14x squared minus 36x plus 45. And this is the polynomial of degree 4 with the given zeros. How do we feel about that?
I mean,
It's
fine.
not hard. It just
It
takes
takes a lot.
At least it's just factoring, not anything.
It's very difficult.
Any major issues with anything we did to build this polynomial? No, we're okay?
Yes.
You guess. Okay, so this leads us directly into another theorem.
Is this the long one?
No.
Yes.
The theorem is long, but not the problem.
Everything is long.
Not everything is.
Is 2 plus 2 really that long?
Yes.
Yeah, we need 2 plus 2 like that.
Do math.
That's when you plug in 2 plus 2 into the calculator just to make sure you're not.
I've done that.
I do that every time. If you don't do that, what's wrong with you? You can count with your hands. What's your step? I can only count there. You can count your hands.
Okay, so this is the title of our theorem. It is a theorem on expressing a polynomial as a product of linear and quadratic factors.
How do you have a negative degree?
The question for a different day.
What is?
Yes, how do you have to have a negative degree? this theorem says that every polynomial f of x with real coefficients and positive degree n can be expressed as a product of linear and quadratic polynomials with real coefficients such that the quadratic factors are irreducible over the set of real numbers.
Need some water? Might need like 5 more minutes like that.
I'll give you a minute. Factors that are irreducible over the set of real numbers means that I would get imaginary numbers or complex numbers if I were to try to take the factors of that. Okay, so irreducible means I can't have imaginaries anywhere in here. If I were to get imaginaries, I had to leave it as the quadratic that it originally was. Okay?
You think this is under the pen?
Maybe.
Right.
Honest answer.
Have like a 4th page left.
If I start over here and work my way,
For maybe the first part, we'll see. Okay,
should I just flip over?
no, you can start it on that side, you're fine. So it says to express this polynomial as a product of, we're gonna do 2 different products here. The first product we are going to find is this polynomial in terms of linear and quadratic factors. Or linear and quadratic polynomials, sorry. This means I'm talking about linear and quadratics with real coefficients that are irreducible over a set of real numbers. So I can't have any imaginary factors in this portion. First thing I'm going to do is I'm going to go ahead and I'm going to rewrite the polynomial that I'm dealing with. And I'm going to figure out the best way for me to factor this, or to start factoring this. Anybody have an idea? Molly? Grouping. So I'm going to group these first 2 terms together, and then I'm going to group my second set together. And I'm going to ask myself, okay, what do these first 2 terms have in common? X cubed. So I can go ahead and take that out. When I do, I'm left with x squared minus 4. That seems like a really good thing. I can deal with that. My goal then is to factor something out of that second grouping to make what's inside match what I already have in this factor. What do I have to take out of that second grouping? Nothing. So we say 1 because it's already x squared minus 4. Since I've done this, it will allow me to rewrite this as the product of 2 binomials. Those binomials are the factor they had in common times what I took out of each of those factors. So I have x squared minus 4, and I have x cubed plus 1.
Wait, why is there?
Because I took a 1 out since there was nothing that could technically come out. It already matched what I wanted, but I had to take something out, so I would have a second term in this binomial.
No, wait.
But it's already perfect, just take a 1.
Not in the
Can I factor either of those nicely?
Yes.
Which one? Okay, which one will be the easiest? The x squared minus 4, this is a difference of squares, which means it's going to factor into the same number twice, but one's going to be positive and one's going to be negative. What numbers are going to factor into? X plus 2 and x minus 2. for my first binomial. What about this x cubed plus 1?
That's different.
It's difference. No, it's not difference in cubes. So I don't know if you can do it.
It's the sum of cubes, and I absolutely can. This was a special case that we learned about last year. This factors into the root of each of my cubes with the sign of the original problem times what's left with the opposite sign of the product of my factors. So x cubed plus 1 factors into x plus 1 times x squared minus x plus 1. The good news is I'm almost done because I have 3 linear factors. All I have to do now is decide if x squared minus x plus 1 is irreducible over the set of real numbers, or if I can factor it out some more. How do you think I'm going to do that? We could try to factor like a CB chart, you know, or I could use my foolproof quadratic formula. And if I get a negative under my square root, then I'm done because I cannot factor it anymore then. So let's do the quadratic formula.
It's not foolproof. I'm a fool.
Wait, is this where I need to flip over?
Do you still have room? No, keep going. Keep going. Fill every line. Okay, so I'm going to take this quadratic and I'm going to decide, is it going to have real zeros or is it going to have complex zeros? If it has complex zeros, then this right here is my final answer for part A. If it has real zeros, then I need to factor this or find the zeros and write them as factors, and then I'm done. So we're going to quadratic formula this. When I do quadratic formula, my A value is 1, B is negative 1, and C is 1.
What?
I just pulled the coefficient from in front of each of those terms. Quick question. Do I need to do the entire quadratic formula to figure out if this is going to be imaginary or not? Just the b squared minus 4ac. What do we call that? Come on, it's been on a test and a quiz.
Square root. That's what it is.
The discriminant.
Sure.
We've never heard that word
Discriminant.
ever.
You've heard it at least 10 times.
I've never heard that word.
I
in my
promise.
life.
We had it on.
Never.
And we learned it last year.
Well, you see.
Okay, yes, we did.
Yeah, exactly.
Discriminant. B squared minus 4ac. It is the value that is underneath our square root in the quadratic formula. Why is this going to be helpful in determining if these are real or complex factors? If you get a negative, it's going to have an I in it. If you don't, we're good to go. So let's go ahead and do our b squared minus 4ac. B is negative 1. A is 1. C is 1. I go ahead and I simplify it out. Negative 1 squared is 1. 4 times 1 times 1 is 4. 1 minus 4 is negative 3, which tells me that I would have a negative 3 under the square root in my quadratic formula, which means I would have an I in each of my zeros, which means that this is irreducible over the set of real numbers because I would get a complex answer. So this is the answer to part A. This is my polynomial written in terms of linear and quadratic factors that are multiplied together, and they only contain solutions of real on the real side.
So you want it to equal negative.
No, because if it didn't, I would just continue factoring.
Oh, so either continue factoring
Or we stop.
let's stop the other way.
It will stop either way after we finish this one, yes. But we didn't have to finish it because it would have given us complex answers. So that was part A. Part B then is going to ask us to factor this into the product of linear polynomials, which means I don't care if they're complex or if they're real.
So just
The good news is
after that.
I'm starting from here, so I'm already well over halfway done. I'm just going to have to finish out the quadratic formula and find the imaginary factors for that quadratic. So this is part B. I would like to express it as a product of linear polynomials. have a starting place where 3 of these are already linear, and I will just have to take the zeros of that quadratic and express them as factors. Which means I have to do my quadratic formula. So I do my quadratic formula, and I get 1 plus or minus the square root of -3, because we already did the math up there, over 2 times my a value of 1, which is just 2. Can I reduce that at all? So my zeros are 1 plus root 3 over 2, and 1 minus square root of -3 over 2, right? We can still do the I. Not forget about that. Okay, this is not a simplified form. So I have 1 plus or minus I times the square root of +3 over 2. That is simplified. So just like before, I'm going to take my zeros and I'm going to rewrite them as factors. Anytime we get a 0, when we change it over to a factor, we just subtract whatever that 0 is. Okay, so this, written in factors, oh gosh, is going to be x minus 1 plus I root 3 over 2, x minus 1 minus I root 3 over 2, and then my 3 original linears.
Well, x minus.
No, that one's plus. Yeah, we always do x minus whatever our 0 is. Okay, because this would be x equals 1 plus I root 3 over 2.
Oh.
So when I move it over, it always becomes minus. Just if it was already negative, then it would go positive. This is an acceptable stopping place. However, if you wanted to finish simplifying it, we could split this complex number up into 2 terms and distribute the negative to each of them. That is your choice.
You ever have to do that?
No, this is an acceptable place to stop.
Oh, that's good.
Okay,
I can say we can continue that.
you could split this into 2 terms and distribute the negative. So this would become x minus 1/2 minus root 3 over 2I, and then x minus 1/2 plus root 3 over 2I, and then those 3. That would be the simplified version.
I would do that.
Either one is fine. I'm okay with either. This is where most people like to stop. Questions, concerns, or issues with that? How fried are our brains right now?
Yeah, let's go.
Super.
I am not fried right now.
Show me 1 to 5. How fried are we? We're also almost out of time, which is extremely sad. Okay. This is a great place to stop because the next example is the one that takes a hot minute. I do want to write the theorem that we'll be using starting next class, though, just so it's already written.
I don't think you do.
I really, really do.
Really don't think you do.
Okay,
Do you really I think you want to save it till next
and then I will stop. I won't do the example.
Wait, what? We're doing
No,
what?
I think you want to save it.
We're writing the theorem. So this is the one that we will start next class with. And it is the theorem on rational zeros of a polynomial.
C over A.
What? C over D.
D.
Yeah.
Oh.
The D. I don't know what you mean now. Just leave it, okay? Just trust me. Trust the process.
It stands for Durian.
There you go.
How long is this?
We're almost done.
These theorems are gonna take up like half.
Okay. So this theorem says that if the polynomial f of x has integer coefficients and if c over d is a rational zero of the polynomial such that c and d have no common factors, so they're in reduced form, then the numerator c of the zero is a factor of the constant, which is our last term that has no variable. And the denominator d of the zero is a factor of our leading coefficient, so the number on the term of the highest degree. So basically, this is how we build our table of possible zeros, and then we narrow it down using all the things that we've already learned. This is also called the rational root theorem. That's what I like to call it. This is where we will stop today. And then we'll pick up tomorrow with an example.
Oh God.
And a little recap, because I definitely am not gonna have this episode.
Your homework is 5 questions. Some of them, at least 1 or 2 you might be able to do right now. The others you'll have to wait. My computer says 26, but it's not 26.
I'm gonna tell her. I'm filled with excitement and joy.
Excitement and joy.